For centuries, people have looked up at the night sky in wonder. Though, in this modern age, our models of the cosmos have become quite dense, the fundamental sense of wonder and curiosity still remains. What makes these beautiful stars burn? What do we see beyond a pinprick of light? After years of research and experimentation, countless theories and hypotheses, we now hold the key: nuclear fusion. You've probably heard that neither mass nor energy can be created or destroyed. It only changes form. When two nuclei fuse, the mass of their product is less than the collective mass of the atoms when separated. For conservation to hold, the mass could not have been destroyed. It turns out that the so-called mass defect was converted directly to energy by the interaction of the two fusing atoms.
You see, fusion is a very situational process in that it needs extreme conditions for it to occur. These conditions are so extreme that they don't actually occur anywhere on Earth naturally. We need extremely high temperatures, we need very, very intense pressures, and we also need the proper fuel.
To achieve fusion like that in the center of our sun, the temperatures of the elements need to exceed 10 million Kelvin, or equivalently 28 million degrees Fahrenheit. To put it in perspective, the average industrial furnace used to melt steel burns at about 2000 Kelvin. To achieve the threshold of fusion, we would need a heat 8,000 times hotter than an industrial furnace, all centered on our fuel source. Even if we were somehow able to excite this immense heat, we would still need tremendous pressure to keep the atoms from dissipating. For fusion to occur, the atoms must be as close together as possible. At the temperature scale of fusion, each atom carries enormous amounts of kinetic energy, which, by the ideal gas law, causes outward pressure as the atoms attempt to escape. The pressure required to keep the fuel confined and force atoms to collide with enough energy to fuse is enormous. Lastly, we need the right fuel. The lighter the atoms are, the easier they are to confine and force together. After the Big Bang, the conditions in the early universe only allowed for the creation of very simple forms of hydrogen and helium, the lightest of all elements. This abundance provided the perfect fuel for stellar fusion.
With all this in mind, we look to the stars once more. Our closest neighbor is the Sun, a brilliant body many times the size of our own planet. The immense mass of the star exerts a gravitational pull which compresses the hydrogen and helium at its center. This crushing force is so extreme that the incredibly compacted core is a scorching 27 million degrees Fahrenheit and a devastating 250 billion atmospheres, furiously fusing the elements therein. Let's zoom in to see exactly what's happening on the atomic level. Let's take a look at one of the simplest forms of fusion in stars. It's called the proton-proton fusion chain. The chain begins with two individual protons stripped of their electrons due to the star's high temperature. These are both positively charged bodies, thus they repel one another. Similar to forcing two like poles of a magnet together, their mutual repulsion becomes stronger the closer they get. However, if the two get close enough, a new, immensely attractive force takes over, known as the strong nuclear force. This force is more than strong enough to hold these protons together, forming a larger, uniquely different nucleus than the two used to form it. What's left is a deuterium nucleus, hydrogen with an extra neutron. Soon this nucleus will fuse with another proton, forming a helium-3 nucleus, and finally, two of these helium-3 nuclei will fuse to form a helium-4 nucleus. Through one iteration of the chain, a total of 48 times 10 to the negative 30th kilograms is converted into only about 25 megaelectron-volts of energy. That doesn't seem like much. It's about a billionth of the energy of a typical static shock. However, the fusion in the Sun converts 4.3 billion kilograms of matter into energy every second. The Sun's fuel, though abundant, is by no means infinite. What happens when all the fuel runs out?
You see, a star's life is actually a very graceful balancing act between the inward crush of gravity and the outward pressure caused by the fusion in its core. You see, eventually the star will run out of hydrogen to fuse, and when that happens, it'll compress under its own gravity and begin fusing helium. This process will continue once the helium runs out, and it'll begin fusing heavier and heavier atoms until eventually it reaches the point of no return. That is, iron fusion. As soon as a star creates iron in its core, it is no longer able to sustain itself because iron is energy deficient, which essentially means that the star has to put more energy into fusing iron than it actually gets from the fusion process. And so once that starts to happen, gravity will eventually win this battle between outward pressure and inward pressure, and the star will begin to collapse under its own gravity.
Most star deaths are quiet. They simply collapse until their nuclei can't physically get any closer together, forming a white dwarf. But really large stars literally go out with a bang, a cosmic fireworks display known as a supernova. For these stars, the outer layers converge on the iron core and actually rebound explosively, scattering the elements formed by that star. The energy of this explosion fuses heavier elements, introducing trace amounts of every element on the periodic table into the vast cosmos. This scattered debris spreads throughout the universe, seeding it with the fundamental building blocks for planets, stars, comets, asteroids, and everything we see around us today. So the next time you look up at the stars in awe, know that those shining bodies in the distance are more than just specks of light in the pitch. You are looking at the cosmic factories that brought life to the universe.